Okay, now we're ready to talk about a few important propositions of conditional probability and some really useful rules. So we're going to start off with a few propositions here. Okay, the first one is the conditional probability of A given A is 1. Okay, so really you can think about this intuitively, or if we go back to our definition, just mathematically, just to make sure. Okay, so A intercept with A over probability of A, which is PA over PA, which is 1. Okay, so not surprisingly, but also just think about it intuitively. The conditional probability of A given A, well, given that A happens, the probability A happens is 1, right? So that's not a surprise, hopefully. The second one is that the conditional probability of A complement given A is 0. Okay, so this, let's talk about it intuitively first. If A happens, and then A complement cannot happen. Okay, so that's why the probability, conditional probability of AC given A is going to be 0. Going back to the definition. Okay, so now we know it's A complement intercept with A over PA. Okay, and then the intersection, we know that the intersection between A and A complement is always the empty set. So empty set has probability 0. Okay, so then when you divide it by a non-negative value, like a positive value, then it's going to be 0. The last one is the conditional probability of A complement given B is 1 minus the conditional probability of A given B. Okay, so this actually, if we take out the conditional probability like the B over here, if we remember, I think the complement rule without talking about any of the, so just recall the complement rule that we have seen before is that the probability of A complement, right, equals to 1 minus probability of A. Okay, that's what we covered in chapter 2. Okay, now we're adding the conditional everywhere. Okay, and I will just say that, well, it's no different in terms of the results. Okay, and I will encourage you to think about, well, and try to make sure that you understand how you can show that this is true. Okay, I will also mention that the textbook is a really good resource, especially for the examples that they cover in those chapters. So I'll leave this as an exercise, and then if you have questions, check out the textbook or visit office hours to make sure that you get this right. All right, and then I'm going to cover one very important rule, and I think many of us actually know this intuitively already, but now let's put it back into a formal definition and then bring back our familiar example before. Okay, by the definition of conditional probability, the joint probability of A and B is, okay, so now notice we're using new term here, joint probability of A and B. Okay, and in fact, it's written as what we are talking about in the numerator when we're defining the conditional probability. Okay, so probability of A intersect with B, that is the same as joint probability of A and B, meaning that we're looking at the probability of A and B happening at the same time. Okay, that's why we call it joint. Okay, at the same time. Okay, so if you recall that our definition of conditional probability has this form, right? So if I rearrange the terms a little bit, I bring this to the left-hand side, then we have this particular result. Okay, so joint probability of A and B is the product of the conditional of A given B multiplies with the marginal, actually what we call marginal, okay, only about one event at a time. So it's going to be the product of the conditional and the marginal. Okay, so, well, of course, another way you can do this is to have B given A conditional times probability of PA. Okay, we're going to see a lot more about this once we get to the Bayes rule, because the key of Bayes rule actually is lies in here when we're talking about conditional probability, but we'll leave that for later. And also, you can generalize this to multiple events. Okay, let's just say in general, like n events, then we're able to do the chaining of probabilities. Okay, so the notation here, as you can see, is that we have n different events. Okay, and then we're looking at the joint of all of them. So we're writing all of this intersection. Okay, so each AI is a event. Okay, we have n of them in total. So joint of that, okay, notice that, well, if I start with a margin of A1, okay, and then I can actually get the joint of A1 and A2 by doing the marginal times the conditional. Okay, this is what we have over here. So if I multiply this two, we know that we're getting A1 and A2. Okay, sometimes it's also written as A1 comma A2. Okay, this could be helpful because now you see that once we move to the third term, okay, we're looking at A1 and A2 both are being conditioned. Okay, so now we apply this one more time. This, the product of the three terms becomes this. Okay, so not surprisingly, if you keep going, okay, you're gonna get to the final term, and then once you put everything together, you're getting the joint probability of all of them on the left-hand side. Okay, and I will also mention that here, the ordering of the A1 and AN, A1 through AN, it's pretty arbitrary. Okay, in particular exercise, which we're going to turn to one of them now, you will have to figure out like how you want to do the chaining per se. Okay. All right, so the example that I want to introduce is here. A box contains 8 white balls and 4 black ones. 3 balls are drawn at random without replacement. Okay, so again, key term, at random without replacement, meaning that we take a 1 ball out and we don't put it back before we draw the next ball. Okay, so the question, 2 parts. What is the probability of getting, okay, so here it's saying that the first one is white, the second one is black, and the third one is black. Okay, and then the second question is, what is the probability of getting black in draw 2? Okay, so the second one is probably a little bit more sophisticated here. But let's start with the first part. The probability of getting the first one white, the second one black, and then the third one black. Okay, so of course, we might be able to work this out without knowing about conditional probability, right? But I just want to say that the approach that we used to take thinking about this, especially in the introductory lecture, if you remember some of it, we are unconsciously to some degree using the conditional probability. Okay, so let me put this now in a more formal way. Okay, we're actually using the multiplication rule here as well. So the joint, okay, the left-hand side of the first one being white, second one being black, the third one being black, is the marginal of the first one being white, okay? And then conditional, right? The second one is black, given that the first one is white. And then the third conditional, let me just add a comma here, B3, given W1 and B2, okay? So now I express this more formally, as you can see, but like if you look at the solution, well, this might look very familiar because we know that, well, for the first one to be white, we have 8 out of 12. That's the probability, right, of getting the first one white. And we know that when we move to the second one, we have to subtract, right, because we already have chosen one of them. So we are doing 12 minus 1 equals to 11 in the denominator. So, and then 4 is the number of black balls I'm able to choose from, right? And then when we move to the third, well, it's 10, right? And then 3, because one of the black balls was selected already. Okay, so the answer, like I said, the solution looks pretty familiar, I think, but really, when we are writing that down, even in the past, we are using the conditional probability definition, okay, and the concept as well. And in this case in particular, we're using the multiplication rules pretty extensively, okay? All right, the second one is, second part is interesting and probably a little bit more challenging. Okay, what is the probability of getting black in draw 2? Okay, so let's see. In order to get the second one to be black, okay, it feels like, well, it's also conditioning on the first one, right? Like we don't know what about the first one. So if the first one is white, then the probability of getting the second one is black is probably different. And that is a conditional probability, just as the way that I was talking about it. And if the first one is black, then the probability of getting the second one black, which is conditioning on the first one being black, is also going to be different from what we were talking about earlier. Okay, so now let's introduce this. If we want to consider draw 1, okay, because we know that that is a conditional information for us in order to know about the second draw. So it could be W1 or or B1, okay, and notice that we highlight here they're disjoint, meaning that they cannot happen at the same time, okay? So we know that, well, the conditional probability of B2 given either W1 or B1 is going to be different, okay? However, notice that, well, once we work that out, we're able to use the multiplication rules. And then eventually we're able to get the probability of B2 because, well, the first one could either be white or, right, be black. And there are only two possibilities. So once we work out the joint of W1, B2 and B1, B2, we're adding them up because we only have these two possibilities. So we're adding them up to get the final probability of B equals to B2, okay? This, as we know next, the next topic, as we're going to talk about it soon, is the law of total probability, okay? But here, intuitively, let's make sure that we understand it, that because there are only two outcomes for the first one, all right? So and then we know that B2, conditioning on the first one, once we get that worked out, we're able to get the joint of the two. And because the joint of the two, joint of the two separately for the two different cases, depending on the first one, exhaust all of the possibilities, right, for the first one, then we're just going to add them up. And then each of this, as we know, is what we have worked on before. Okay, so one thing interesting, let me put it in this way, is, well, it's going to be 1/3 over here. Okay, and maybe let's see if you're curious and thinking about, well, what if, does this ring a bell to any of the values or any of the scenarios that we're looking at right now? Okay, and I will leave that for you. For example, like I was going to give a hint really quick. We have 4 black ones. Okay, so actually, well, let me put it this way. If you look at this value, well, it's just like 4, the number of black ones over the total, right? Over the 12. Yeah, it's a coincidence that, well, we don't even need to know what the first one is, and then eventually the second one, well, given what we're looking at here, is actually just the marginal probability of the black one over the total. Okay, so think about that. And next, we're going to move to the law of total probability, which is a generalization of this result. Okay, but regardless, here we focus on multiplication rule, and then of course, based on the conditional probability. And then we have seen the example of chaining, right, of 3 different events through the conditional probability, but you can also just keep going of so many different chain probabilities if needed be, okay, given the question itself.